Hello everybody, welcome to our fourth video together now. Today we're going to go over chapter P4, which covers inverse functions. We're going to do a quick review of that. The objectives for this video are that we learn how to, or remember how to verify that one function is the inverse of another, and that we remember how to determine whether a function has an inverse function. You'll see I crossed out one of these objectives. Don't worry about this one. We're going to cover this in that next video that I promised you guys, where we would review a few trig concepts. So let's get started. The first thing we're going to talk about is inverse functions. And what we should know or remember about inverse functions is that we can algebraically derive the equation of an inverse function by switching x and y and solving for y. This is just a quick reminder of how we get inverse functions in the first place. So for example, we're going to go through a few of these. So say that we want to find the inverse of f of x equals x to the third. Now remember that this f of x is really the same thing as y. So up here we need to switch x and y to find our inverse, we remember? We're going to do that by remembering that f of x is actually just y. So if we switch these two, we get x equals y to the third. And then if we solve for y from here, we can take the cube root of both sides. We see that now y is equal to the cube root of x. And so up here, when we report our answer, remember that inverse notation looks like this. The inverse of f of x is f to the negative 1 of x, and we can say that that is equal to the cubed root of x. Alright, interesting. X cubed was our original function, and its inverse was the cube root of x. Interesting. Interesting stuff. We'll talk about that in a second. Next example. So same thing, if we were supposed to find the inverse of a function, we'll call this one f of x equals x minus 5. We do that same thing. We know we're starting with y equals x minus 5. We switch our x and y's. We solve for y. We add 5 to both sides. Okay, so now we know our inverse is x plus 5. So when we report that, we say f to the negative 1 of x is x plus 5. Interesting stuff. Check this out. Our original functions and their inverses. Take a look at what's happening here. X cubed, its inverse is the cubed root of x. Essentially, what we're seeing here is that these inverses kind of undo the original functions, don't they? If we added 5 here, we'd get x by itself. If we cubed rooted here, we'd get x by itself. These inverses, when combined with their original functions, undo the original function. Pretty interesting stuff. I want you to jot down just 3 other key points about inverse functions down here at the bottom. Let me move my paper down. Okay, so remember that the domain of a function is the same as the range of its inverse. And the range of a function is the same as the domain of its inverse. And when we think about it, that makes sense because the inverse, by definition, is just those x's and y's switched. So it makes sense that the range is its domain, and its domain is the range, and vice versa. It makes sense that those values flip-flop. And the last note I want you to jot down for this page is that functions and their inverses reflect over the line x equals y. We can do a quick illustration of that right here. So say we had the coordinate plane, and here's the line xy. If you don't remember, it's just that exact diagonal one right down the middle. Just kind of dash line it right now. And say that we had a line that passed through the intercepts at a y-intercept of -5, and say it had an x-intercept of 2. Or, yeah, no, that'll work. We'll do it. And then we connect those points, and we draw our line. I'm going to kind of draw it out here so we can see where they cross each other later. Okay. So say that was our line. We'll call this f of x. Awesome. Now remember, the properties of inverses mean that our domains and our ranges switch, which essentially means that our x's and our y's switch. So if our original function had a y-intercept at -5, then our inverse of this function is going to have an x-intercept at -5. So all the way over here at -5, it's going to cross the x-axis. And then vice versa, our original function had an x-intercept at 2, so our inverse is going to have a y-intercept at 2. Oh, 0, 2. And then we cross those points with our line. Pardon me for not making this very straight. I'm just trying to illustrate a point here. Okay, and we could call this one f to the -1 of x, right? Our inverse. And you can see that these two lines cross each other, not the most artistically correct, but we get the point. They cross each other over that y equals x line. They reflect each other. All right, moving on. To our next topic, which is how we verify inverse functions. And it's going to be important to remember what we just talked about. Verifying inverse functions. All right. Verifying inverse functions. So, for example, say we were asked to show that the functions f of x equals x squared plus 1, where x is greater than or equal to 0, and g of x equals the square root of x minus 1 are inverses or pardon me, inverse functions of each other. Now, remember when we said that inverse functions essentially just undo their original functions. And if we combine them, then we just get x. So we can prove that two functions are inverses of each other by doing composite functions, which we reviewed in the last video. So we can prove that these two are inverses if we start to do f of g of x and g of f of x. So let's start with f of g of x. And if we did that, we would get f of radical x minus 1, which would look like radical x minus 1 squared plus 1, which would just become, the square would get rid of the radical, we'd get x minus 1 by itself, and then x minus 1 plus 1, we would just get x. Okay, that's looking good so far. Let's check the other way. Let's try g of f of x. And if we did that, we would get g of x squared plus 1. And if we put that into the function, it would look like this, where we have x squared plus 1 minus 1, all under the radical. And just using some mental math here, we can see that the plus 1 and the minus 1 would cancel each other out, and then we'd have the square root of x squared, which we know to be x. There we go, we proved it. These two functions are in fact inverses of each other because their composite functions equal x. Another question you may be asked in order to verify an inverse may be something like this. So you may be asked to show that f and g are inverse functions numerically. You're going to have to show that numerically, and here's all numerically means. We're going to use another property of inverse functions, the one we talked about with that graph we just drew, where we know that if one function has an x coordinate, then its inverse is going to have that same y coordinate, and vice versa, and their domains and their ranges flip-flop. So here's what we can do. If f of x equals 3 minus 4x, and g of x equals 3 minus x over 4, we want to prove that they're inverses. What we can do is we can plug in a value to, say, f of x. Let's plug in 1. 1's an easy number to plug in. If we plugged in 1, we would get 4 times 1, which would be 4. 3 minus 4 would get us negative 1. Awesome. So now we have a coordinate pair, right? We have for the function f of x that there's a coordinate 1 comma negative 1. That means that if g of x is an inverse, the coordinate negative 1 comma 1 has to exist. So let's plug in negative 1 to our g of x and see if we get positive 1. If we plugged in negative 1 on top, we would get 3 plus 1. 3 plus 1 over 4. So 4 over 4, which would in fact be 1. That checks out, doesn't it? Our domains and our ranges switched. Now, the last thing I have to show you for this video is the existence of an inverse function. So let me move my paper down. Okay. Last topic. Sorry, I have to bump into the camera every time I want to write something. These guys need to get me a new document camera. Alright, just kidding. The existence of an inverse function. Okay. So we've just talked about how we can verify that an inverse exists. There's another way, though, to think about it graphically. So write this down next to our definition here. A function has an inverse, and I'm going to write the word IFF. And IFF in math just stands for the words if and only if. So a function has an inverse if and only if it is a 1-to-1 function. And remember from our last video that all this means, 1-to-1 just means that it passes the horizontal line test. If a function passes the horizontal line test, it is 1-to-1, and that means that it does have an inverse function. So take a look at this example. We're asked to use the graph of f of x equals 3 minus x over 2 to determine whether the function has an inverse. All right, well, if we graph that line, that function f of x on our coordinate plane here, I know right off the bat that our y-intercept, gonna make some lines here, that our y-intercept is gonna be up here at positive 3/2 or 1.5. And again, that's just because this is the same as saying 3/2 minus x over 2. So our slope is negative 1/2. So if we go down 1 and over 2, make a point. Go down 1 and over 2, and sort of imagine your point out here, and then just connect these two. All right, that's our line. And if we were to test it with the horizontal line test, we can just quickly draw a horizontal line through it. Check it out. It crosses at only 1 point on our graph. So yes, it passes the HLT. It does have an inverse. An inverse exists. A counterexample of this might be the function, for example, f of x equals x cubed minus x plus 1. If we were to graph this function, we can see right off the bat it's a cubic function, which means it's going to be a little bit curvy. And here we are at negative 1, 1, and at 1 here. Okay, those are all the important pieces we needed to know. I'm going to try and, okay, yeah. So if we go up and we curve a little bit, and then it starts to come back down, and then it comes back up, we can see that if we threw a horizontal line through this graph, it would cross at 3 places. It would cross at our negative 1, 1, at 0, 1, and at 1, 1. That is not a 1-to-1 correspondence. There's 3 values of x for the 1 value of y. That is not passing the HLT, so it does not have an inverse. Okay, that's all I have to show you today. We'll see you in class tomorrow. Thanks for watching.